Hello everyone. In today's part, let us start discussion about Newton's laws of motion. Okay, so this is the major part of the dynamics, and dynamics, which is a basic part of mechanics. Okay, so it is very essential to know foundation level what is force and what are the consequences. All these things we will learn under the part of dynamics here. So, under dynamics, major part is Newton's laws of motion. In today's class, let us start discussion about Newton's laws of motion. Okay. So, here how mechanics is classified into parts. First, mechanics, it is major branch of physics where we can deal with the motion of the body. Okay. One part is kinematics, and kinematics is the example, or we can study the motion of the body. What is the reason for its motion, we leave it, and we always discuss about what is its speed, what is its acceleration, what is the distance covered, what is the time after which it will meet. Like that concepts we will discuss in the kinematics. Means there is no reason why a body come into motion, or we don't want what is the reason why body come into motion. That part we will discuss here. Okay. So, in the part of dynamics, why the body coming into motion, okay. So, including that reason we will discuss under the dynamics, okay na. So, that is nothing but it is the study of motion of the body, including the reason why the body coming into motion, discussion under the dynamics, okay. In this dynamics part, major one is Newton's laws of motion. So, let us start discussion about the laws of motion, okay. So, here basically the fundamental phenomena getting by the Newton from Galileo's principles only, okay na, and he gave in the form of 3 laws. And the first one, first law of motion, it is also called law of inertia. Second law of motion, and it is also called law of momentum. Third law of motion, and it is also called action reaction, okay. Now, let us start discussion about the laws of motion one by one. So, here it is only the given part. First law of motion, what do we call? And second law of motion, what do we call? Third law of motion, what do we call? Just now I told you, first law of motion we usually call law of inertia, okay. So, let us see here, just I am writing law of inertia. And next, it is law of momentum. And it is action reaction pair, it explains about, okay na. So, now let us start one by one, okay. So, we begin with the first law of motion, but it is explains majorly about the inertia. So, we will need to know about inertia. What is inertia called, okay na. Let us start discussion about the inertia here. So, what is inertia called, okay. So, here inertia called the resistance of a particle to change its state. That is exactly what we call, that is from rest or from uniform motion, it is called inertia, which is nothing but, let us see here first of all, the resistance of a particle, which means, for suppose a body which is at rest, and it is resistance to change its state of rest into motion, okay. When a body is in rest, it will try to maintain in the rest only, okay na. Suppose when the body is in motion, suppose the one body is moving with some velocity v, supposed to be considered, and it will always move with the same velocity only, and it is resistance to or opposed to stop the motion here. That resistance to the state change concept is called inertia, okay. So, that is what we can discuss here. Once again, definition wise we will take out. So, inertia means the resistance of a particle, okay na, means opposition exerted by the particle, and we do not go like opposition exactly, okay. We just give the statement as resistance only, okay, to change its state of rest or uniform motion. Means if the object is in rest, it will be continuing the same state of rest only. If the object is in motion, it will continue to be in the same motion only. It won't change its state, is nothing but we discuss about inertia. Okay. So, in detail when we discuss, which means actually first law we can generally we can enter if we discuss that point. Okay na? So, there is no force acting on the body, it will be maintain the same state like it is in rest only, it is in motion, then it will maintain the same motion. Okay. So, that is the major explanation of the inertia, and we need to know about the types of inertia here. So, first inertia types, first one inertia of rest, and second one inertia of motion, and third one inertia of direction. Okay. So, what is inertia of rest, what is inertia of motion, what is inertia of direction? Let us see one by one now. Okay. First of all, inertia of rest. Initial state of the body is at rest, the body resists its motion, means body resists motion, that is it. Okay. Suppose when a body is at rest, it is always resist to be change its state of rest into motion. That part is explained by the inertia of rest. Okay. So, here once again I am saying here, initial state of the body is at rest. Okay. Now, the body resists its motion, resists the motion. What we can say, when object is at rest, it resists to coming into motion. That part we can call about inertia of rest. Here you are observing one picture in this one. Okay. So, this picture you can see, suppose all the persons in the bus, they sit in the seats and one person standing in the bus. Okay. Suddenly, when driver came and suddenly bus started and moving forward, suddenly bus moving. So, when bus suddenly moved, then passengers in the bus will be feel a jerk little backward direction. So, what happened, why they are moving backward direction? Here it is only very important point. Before bus start moving, the persons in the bus are at rest, like initial state of the body is rest. Okay na? So, all the persons in the bus are at rest. Bus starts suddenly moving. Bus moving means there is a reason, because engine apply the power and engine give the power, and that is what it is moving. But here at the same time, persons also need to be moved along with bus, but they are opposing the motion immediately, instantaneously they oppose. With a fraction of second they will adjust their motion with the bus only, but during this change is there, no, in that time they feel a little jerk backward. That jerk is due to inertia of rest. Okay. And more examples also we can discuss in this case of inertia of rest. Like example, when you shake the branch of a tree, ripened fruits are going to fall, because the fruit in the branch will be at rest. When you give sudden jerk for the branch, and it will resist to its motion. So, in this one, the whatever the fruit is connected to the branch, that stem will be broken and it will be fall. Okay, this is one example. Next, when you are continuously beating with a stick for the carpet, whatever the dust particles are present in the carpet will be get off. Okay, why? Because when we are beating with the stick for the carpet, so carpet particles are going to be setting into motion generally one by one. Okay, but the dust particle is resist the motion because it is at rest. So, due to that action here, the particles fly off. So, this is also one of the example for the inertia of rest only. Okay. So, likewise these are the conceptual examples we need to discuss about the inertia of rest. Okay na? Once again, inertia of rest means initial state of the body is at rest only, and the body resists the motion, which means the body is in rest. It is a resistance to move immediately, or with itself it resists to move. That is called inertia of rest. Next, second type, inertia of motion. Initial state of the body is in motion, which means, now suppose same example we can take, and we will discuss about second statement also. The body resists coming to stop. You need to understand here, these are the basic terminology you can just consider. Okay. From this you can observe the difference between first one and second one, that is inertia of motion and inertia of rest. You need to say, observe here, the body initially is at rest in the first type, and here in the second type inertia of motion, initial state of the body is in motion. So, we will take the same example. Suppose bus was started here and it is moving continuously for suppose with the uniform speed only we can consider. Okay, now bus is moving. Suddenly driver apply the brake. Okay. So, before applying the brakes, then bus condition was like it is motion. So, initial state of the body is in motion. The same condition we are applying, which means the bus is moving or bus is in the motion. So, when driver applies suddenly brakes, okay na, the persons in the bus fall forward. Why they fall forward means the second statement, body resists coming to a stop, which means as the bus is in motion, persons in the bus also moving with the same kind of state of motion, and when bus stops suddenly, the persons which are in who are in motion, okay na, they are resist to coming to stop. So, that is what they feel a jerk in forward direction. This is the example for what inertia of motion here. Okay na? So, this is one of the example you need to understand, and later on examples also we can discuss here. One point you need to discuss that is when a person is in doing horse riding suppose. Okay na? So, we can take both examples from the horse riding. Okay. So, person sitting on the horse and the horse suddenly starts its journey or running race. Okay, and if the person sitting on it, he was not aware about the starting of the horse or starting race of the horse, then if he won't hold any kind of ropes, then he may fall backward because of inertia of rest, because it is giving a jerk backward. At the same time, when horse is running fastly, okay na, and person is also on the horse running moving along with the horse, okay, now horse suddenly stops and he was not perfect in the horse riding suppose, then there is a chance of that person on the horse will be fall forward. Okay. So, what we can discuss, horse is in motion when it is riding, okay na, the person sitting on it also moving with the horse, but horse stops suddenly and he was not taking appropriate precautions, then he will fall forward because of inertia of motion, because he is resist to stop the motion. Okay. This is one example we can give for inertia of motion. And second one, in sports, in regular cases you can see here, suppose in Olympics, if the running race completes, okay na, suppose a running race conducting here, after reaching the goal also the persons are not stop immediately because of inertia of motion. When they stop immediately after reaching the goal, it is making some changes in the person, okay na, that is not possible also. Okay. So, you need to understand here, the person is in motion, you need to run some distance after reaching the goal also, you can observe this kind of things regularly, okay na. And next this is actually not to do by anyone, so but giving example, if a person getting out from the moving bus, it is against to the rules, don't get down from the moving bus, but example I am saying here and not to follow by anyone, just listen the example, that is it. Okay. So, when person is getting out from the moving bus, getting out from the moving bus means he was in motion when he was in bus. When he was getting out suddenly, he will resist to stop its motion, so he will fall forward. So, that is what he need to run some distance to avoid falling, okay na. This is also due to inertia of motion. So, next a person is getting some distance and he run from some distance to take a long jump. Why can't he start a long jump from the starting point to target means, it is impossible to get the body in motion immediately, okay na. So, when he was running from certain distance, his body is in motion, then he can lift his body with own efforts, then he can jump to such a long distance. This is also we can take the example under inertia of motion. These are the some examples which can illustrate about the inertia of motion. Next, inertia of direction. The body resists the change in direction. Okay. So, he was moving along a straight road suppose in a car, and car takes suddenly turning, then if just bend opposite side direction, okay na. So that's because resist to change the direction of motion is called inertia of direction here. And what are the examples we can learn under this one means many examples are there, and you might play with these examples also. When you just make a cycle stand in the water suppose, and just when you rotate the back wheel, then water contact with the back wheel gets fly off like a tangential path whenever particles are thrown outside. So it look like this here. You just see, when you just rotate a wheel, the water particles which are in contact with the wheel are getting thrown out in the tangential path, okay na. So they are resist to change their directions actually. So next when a person in the car, same example we can take, when a person in the car is moving in straight road, suddenly takes a turn, just he leans direction wise, okay na. If he taking a direction right side, just he will lean left side. So he resists to change the direction of motion. That is one example, okay na. And next when just rotating a stone tying with a thread, and just we can rotating in the circular motion, and if you cut this one, so suddenly it moves along the tangential path, okay na. So that is also here what happened. It moves in the tangential path. Before that it is going to be moving in the circular motion, okay na. So tangential path, why it is going means that whatever the keeping tension will be there, that is not there when you cut the string here, okay na. So these are the some examples for what inertia of direction, right. Only these are the characteristic properties and types of inertia we have discussed here, that is inertia of rest, inertia of motion, inertia of direction. These are the three types of inertias, okay. Let us know more about the inertia basic important points what are. So let us discuss that points. Inertia is a property of the mass of the particle, which means more is the mass, more is the inertia, and less is the mass, less is the inertia. We can just getting from this concept, that is inertia proportional to mass, okay. So this is what one important point. Next we discuss about these concepts actually for linear motion, but for the case of rotational motion, it not only depends on the mass, but also distance from the axis of rotation, and this parameter is generally we can call moment of inertia, okay. Generally you learn about moment of inertia in rotational motion, but here whatever the inertia about we are discussing na, so generally inertia for rotational motion case, it is not only depends on the mass, it is also depends on what a distance from the axis of rotation. So that is actually called moment of inertia, and moment of inertia basic formula we can give as I equal to mr square, okay. But you know more about this moment of inertia in the coming lesson, rotational motion, right. And let us move on to next slide here. Here is the first law, and first law of motion, and it is also called law of inertia, okay, as we just discussed that one. So now what is first law of motion actually? So let us see, every object will remain at rest or moving with uniform motion in a straight line until, these are important, until and unless compelled to change its state, okay, until and unless compelled to change its state by the action of net external force, which means there is no force acting on the body. Suppose example we can see, it is a table, okay. On the table we just place a book, and nobody applies force on the book, then book will be at the rest only. How many days after also we see, book will be there only. That is, a body which is at rest, it will be continuous in the state of rest only, okay. Now one more example we can see, when a ball is moving on the floor suppose, and it is a huge horizontal ground where just we have a moving of a ball on the ground, but after traveling some distance, ball will be come to stop. Why? Because that is because of friction. And if there is no friction between the ground and ball, we can assume that definitely the ball will move continuously, enormously, and that it will continuously to move in the same velocity. So that explains here second statement, which is in a uniform motion, it will be move in the same uniform motion. Okay. So that is happens until and unless there is no external force acting on the system. Once there is external force acting on the system, it will be no more continue in the same state. That is, rest, whenever it is at rest, it is being applied by some force, no? Then if it is capable to make it to motion, then it will move. And a moving particle can be stopped by applying force, then it definitely stop. That this will be happen until and unless if there is no external force acting on the body. Okay. So next, first law can be also stated as, what is the actual meaning of this statement? We can learn in the second point. If the net external force acting on the body is 0, which means F net acting on the body is 0, then the body remains at rest or moving with a motion. I am just, it is a statement for object at rest. Okay, na? So object's acceleration also must be 0. But here 0 acceleration explains velocity constant also. You need to remember, sir. Okay, na? That is, acceleration 0 means velocity also constant. Okay, na? And next velocity may be 0. So that two conditions will come. I am talking about velocity 0, which is at rest. Okay, and how come object moving with a velocity same? So supposed to be take, and if there is no force acting on the body, just now I have given example, a ball is moving on the floor and there is no friction and we don't stop anybody, suppose, then ball continues to be move with the same velocity only. There is no change in the velocity. So that is what explanation for constant velocity. Okay, na? Even F net is 0. Particle, there is a chance of getting constant velocity for the moving body, and velocity equal to 0 also come then when the object is at rest. Okay, na? So these are the conditions here. See, he was kicking a ball, and if he unable to kick or if won't kick the ball will be at rest only. Okay, na? Means there is no force, no acceleration. Okay, so that concept we can take here, and velocity also 0. Next, he was catching a ball actually. Before catching a ball is coming from cricket batting person, suppose. And if he was not catching and if it is moving in the same height, suppose, if gravity is not there, okay, air drag is not there, then ball will continuously to move in the same direction. Okay, it won't change its path also, as you might learn in the kinematics 2D, it moves in a oblique projectile motion. Okay, na? That is happen because of what? Gravity only. If no gravity, ball try to move in the same direction. So then there is no chance to be catched by the person. Suppose he was not catching the ball was in motion. Okay, it will move in the same motion only with the same velocity, but he was applying some force to catch the ball, so suddenly it stops. Its acceleration become 0. So this concept we need to learn from the first law of motion. Once again, everybody, so every object will remain at rest or moving with uniform motion or moving with uniform velocity in a straight line until and unless compelled by compelled to change its state by action of net external force. Okay, na? And it can be studied in the another terms. First law can also be stated as, if the net external force acting on the body is 0, only then the body remains at rest. Means there is no external force acting on the body, then body at rest only. Okay. So let us move into next one. Next property, next quantity, momentum. Okay. And as we go into the coming chapter wise, it is also been called linear momentum. Okay. Here no problem if we call momentum also. But in coming chapters, one more momentum coming, that momentum is actually called angular momentum. So we need to differentiate between both of them. So definitely we need to call this as linear momentum. In rotational motion, you discuss about angular momentum. Okay. So what is linear momentum? Let us start discussion here. Momentum is the quantity possessed by an object by virtue of its mass and motion. Okay. So generally it is called product of mass into velocity, you might know, okay, somebody, but we can define generally mass into velocity, and here by virtue of its mass or due to motion. Okay. So this is what actually whatever the quantity possessed is nothing but momentum. And second way of definition, it is also known as the quantity of motion. This is very, very important, quantity of the motion. And you might seen in the groups, some friends will be discuss. I have seen, I saw a car which is moving very fast and which is very little car and moving with a greater speed. How we can explain? The way of explanation and its size and its speed he was comparing, no, that nature only actually we can call quantity of motion. Okay, na? With what momentum? You might not use momentum, but you are expressing about the same quantity, you are explaining the same quantity with your friends. Okay. So that is what we can say here. Quantity of motion means what? Momentum we need to discuss. Okay, na? And it is actually vector quantity and its units are kg into meter per second. Why? Because its equation generally P equals to mv. Okay. Momentum is indicated by P vector, sir, and mass is scalar and velocity is vector. So product of scalar into vector is also a vector, and that's what again it is momentum is vector we generally indicate. Okay, na? So we can write down here P equal to m into v, where m units are kg and velocity units are meter per second. So that's what we have, kg meter per second is the unit for momentum. Okay. So since it is a vector, no, if you are taking right side is positive, then definitely the same particle moving with same velocity but direction is opposite to first one, you can treat it as minus. Okay. Sir, why should we take always left side only minus? Why don't we take right side minus? Yes, you can. In the question itself, if they are explaining about left side moving initially and later on it is going right side, so initially you take plus and later on you take right side minus, there is no problem. Okay, na? So that depends on you, but you need to aware in which direction you have taken sign positive and in which direction you have taken sign negative, and you need to clear about the sign conventions to solve the numericals. Okay, na? So this is what about momentum, just introduction. Next, momentum change and based on momentum problems we will discuss in the next class actually. Okay, na? Here we just give the introduction for momentum. Why? Because it is necessary to define, to explain the Newton's second law. Okay. So let us start moving into Newton's second law. Newton's second law, it is also called law of momentum, and what explains here Newton's second law? See, the rate of change of momentum, you see, of an object is proportional to net external force, okay, and is in the direction of net force applied. Whatever the force is applied, in the same direction only the momentum change will be happen. Okay, na? So now let us see one condition, that is, if we take a one ball, okay, na, ball of mass m moving right side with speed u, right? In we have just seen in the previous slide, a person is kicking the ball from the rest. Suppose moving ball, if we kick the same ball, moving ball, in the same direction of motion. What I mean, if a person is kicking this ball in this direction, so then is there any chance to move with the greater speed? Definitely we can see greater speed. So it moves with a different speed called v, and definitely v greater than u. Okay, mass will be same. Now momentum is going to be changed because here m into v, here m into u. So whatever the momentum we got here, P final equals to m into v, and where here P initial equals to m into v. Okay. So now momentum is going to change taken place. Why momentum is changed? Because of force applied. Okay na. So direction of velocity change is also right side, and change in velocity direction with respect to time gives you acceleration, and change in change in velocity by time acceleration, and acceleration into mass gives you force. Okay. So according to definition, the direction of net force only means the change of momentum, rate of change of momentum, the rate of change of momentum will be in the direction of applied force only. Okay. So that is in detail we can learn from the equation itself. According to statement, this is F net externals are, no need to consider internal forces. If any forces are present internal, we no need to consider about them. We only consider about external forces. So here we can write down dp by dt. dp is change in momentum and dt is with respect to time. Actually it is called the rate. The rate at which the change in momentum takes place is directly proportional to net external force acting on it. Okay. In physics generally, after removing a proportional constant symbol, we can proportionality symbol we can use a constant. Okay. F equals to k into dp by dt, where p equals to m into v or m into u. Sorry, this is m into u. Okay na. So this is m into v, this is m into u, right. So here we can see this is mv. So just I am taking a intermediate any velocity, any time velocity mv. So we can write m outside because we consider mass is constant. Actually this formula can be applied in either case. Okay, that is mass variable, mass constant. In either cases we can apply the same concept. We will discuss here. Okay na. So from here onwards, if we take mass as constant, let us explain first. Mass is constant I have taken here, then velocity been changing. So change in velocity with respect to time gives you acceleration. So definitely k value I am taking as 1 for the point mass and unit masses cases. So we can take dv by dt as a, then m into a. So this is the expression for the force we can get from the second law of motion. Okay. So let us see what happens if mass is variable. From here only we can change the answer. That is, I am taking k value equals to 1. Okay. So that is m into dv by dt plus v into dm by dt. So this is the actual expression for the second law of motion for many cases problems to be solved. And if you do not want to get any confused, then definitely you can consider whatever I have explained first one. Okay. So that is mass is taken as constant only. Okay. So for high level problems to solve, sometimes they consider mass as change and sometimes they consider as mass as constant. Okay. So suppose variable mass case, definitely there is a velocity constant. Okay na. So variable mass means mass is not a constant. Okay na. So velocity will be constant in such case. Okay. So now what we have considered here, assuming mass is constant. Okay. How we have solved this question I will explain from this answer also. What we have taken, mass is constant. Here mass I am taking constant. Constant differentiation gives you 0. So then this term becomes 0. Again this term only you get. That means here from here this term you get. That is m into dv by dt, m into dv by dt. So there is no problem, you express the same equation in this term or in this term, there is no problem. Okay na? But you need to consider mass is constant, then dm by dt equal to 0. Okay na? And mass is variable, then this term also to be included. If suppose velocity constant, if mass is variable and velocity constant, then this term becomes 0. Okay. So in same question there is a less chances to come either equations used in the same part. Okay. You can use first part of the equation or second part of the equation depending on the question, right. So mass is variable, then definitely there is a chance to giving velocity constant, then this term become 0. Then equation stands for F equal to V into dm by dt. Okay na? This explains also F value or force acting on the system. Now let us know deeply here, that is Momentum is vector generally, so acceleration is also a vector, then F is also a vector. So we can take along x, y, z axes their components. What happen? Momentum component as dpx, acceleration component as ax, okay, and here same y direction and z direction, and which explains about the dpx by dt gives you max, and which explains component of force along the x axis. Same way y axis and z axis. Okay. So now the very essential point to discuss Newton's law to apply, that is Newton's second law of motion is applicable only for point masses. Okay na? Point masses for the case situation only we can apply this Newton's second law, right? So let us move on to the next slide. Importance of second law, right? So this law gives us the measure of force. We can able to find the force, or we can able to measure the force. Just now we discussed F equal to ma, okay. The unit of force is defined from this law. Unit force is very important. Unit values are very important, okay na. From the concept you can see F equal to ma, okay. If 1 kg mass I took and acceleration is 1 meter per second square, 1 into 1 gives you 1 Newton, and generally unit force we can call here, okay. The magnitude of force is equal to 1 Newton, then it is generally we can take as unit force. Now next, this is the real law of motion, okay. This is the real law of motion because both first and third laws can be derived from this one. First law, how, like if there is external force 0, okay, then definitely A equals to 0, okay. This is actually first law. And third law we can say that force only we can take, okay na. F action equal to minus F reaction, we will discuss in the coming classes how we can solve this equation, but with the help of force only we can derive third law, okay na. So that's what second law only true. Why? Because we can derive the first and third laws from the help of second one. Next, force cannot change the momentum along a direction normal to it. That is, here you can see direction normal to it. What it means? Let us see. A particle is moving along this direction, okay na, and suppose a force applying along this direction, okay. So these both are perpendicular, right? So you can see force cannot change the momentum along a direction to normal to it, which means force is not acting normal direction. Suppose force is acting along the direction of motion, means just now we have taken previous example, ball is moving right side and next ball is moving right side only after application of force in the right side direction. So what is the value of force in the direction perpendicular to it, okay na. So that is, here whatever the value of force in perpendicular to direction of motion will be 0, okay. Means velocity change in the direction normal to the original motion, generally we can take it as 0. Why? Because component of F in normal to this one we can easily get F cos 90. So that explains about 0, which means perpendicular direction there is no force acting, which means definitely when there is a force acting in a particular direction, so there is a change in velocity, and having some mass definitely change in momentum. But in this situation, perpendicular direction there is no change in the momentum, that is component of velocity normal to the force does not change. What I explained here, component of velocity normal to force does not change. Suppose force acting right side, velocity also right side, okay, then velocity change in the direction of force, not along the normal to the force, okay na. That explanation from the third point. This is what actually importance for the second law, okay. Let us move on to the next slide. what is actually force, okay, more about the force, right. Here it is a push or pull that changes the, tends to change the state of motion. If the force is not acting, or just we don't push or we don't pull the body like this, okay na, if we don't push and we don't pull the body, then it will be in the rest only, okay, means it is tend to change the state na. We are not capable to pull, suppose, but we are trying to pull it, so something we are trending to move, right. So in that situation, what we are exerting force, actually what we are pushing, that pulling, that concept, object, that explains about force, okay. An external agent which is tend to change the body's state of rest to motion or motion to rest, okay. Next, force can change the direction of motion of a body, which means if the ball is coming from here and if we having a bat with a hand, so if you hit the ball in this direction, so ball direction will be changed, that is one of the concept. And speed of a body also, okay, if it is coming in with some velocity and if we push or just in this direction with a greater force, its velocity is going to change, speed also going to change, okay. Even shape of the body, we can break some objects, suppose, okay na. So in such case we can say change in the shape of the body. Next, force is a vector quantity. So we just now I discussed here, F equals to ma, a being vector and F must be also vector quantity, and it has both magnitude and direction, okay na. And unit of force will be taken as a Newton, right. So this is the symbol actually N. So next, here net force acting on the body, how we can take, actually it is a vector, no. So then definitely the vector sum of all the external forces acting on the system represents the net force on the system, okay. Vector sum, why? Because let us see, it is acting in certain particular direction, it is acting in particular direction, it is acting in particular direction, then definitely vector quantity means we need to add them vectorially, we don't add simple algebraically, okay. The vector sum of F1 plus F2 plus F3 so on, we can express here the net force acting on the body, we can find out, right. So here F net, if it is 0, whatever the force after adding vectorially also we got 0, then the object will be continue to do what it has been doing, means if it is at rest, rest only, if it is moving with constant velocity, it will move with the same constant velocity, okay. So this is about F net acting on the body. Next, let us move on to the next slide. Here different units of force, just now I have given Newton is the SI unit, but some gravitational system of units also there. So we discuss about the different unit systems for the force. Let us see, SI unit is actually we can take as Newton, and CGS unit of the force is taken as Dyne. So further we can extension this one. So generally F equals to, we have formula ma. So mass is expressed in terms of kg, acceleration is expressed in terms of meter per second square. That is 1 Newton equals to 1 kg meter per second square, okay na. And here Dyne is CGS system, so definitely 1 Dyne equals to, we can write these values in CGS system, kg become gram and mass become meter become centimeter, second will be same, so gram centimeter second square, 1 Dyne is equivalent to, okay. So next, relation between Newton and Dyne, actually 1 Newton equals to 10 power 5 Dynes. Let us take the relation here definitely. So first 1 Newton equals to 1 kg meter per second square, okay. Now we are converting into Dyne, no. So definitely we need to convert into grams. So how many grams in a kg means 10 power 3 grams. How many centimeters? 10 power 2 centimeters per second square. So which explains 10 power 5 gram centimeter per second square. Gram centimeter per second square is also written as Dyne. So which is 10 power 5 dyne. Okay, so this is 1 Newton equals to, right? So that is what we have proved, and 1 Newton is equivalent to 10 power 5 dynes. Okay, so now gravitational units are practical units for the force here, which means if you hold an object in your palm, okay, na, it will exert some force on your palm. Okay, definitely. Okay, sir, I just hold the object, no force acting on it, na. So how it is exerting force? You feel that. Suppose if you are holding object, okay, na, if it is not applying force on your palm, if you just take out your palms, then object should be stand here only. Okay, na. Will the object be present in the same position? Definitely no. It will fall down. So that's what you are applying some force indirectly on the object upward against falling. So by the mean of this one, object exerting force. How much force it is going to be exert on your palm, that is in terms of gravitational system of units we can measure. Suppose 1 kg weight or 1 kg force, 1 kilogram object it is hold in your hand and it is being accelerated towards the earth. With what acceleration towards the earth? Definitely 9.8. Okay, na? So then 1 kg weight is also equivalent to 9.8 newtons. So 9.8 newtons it is going to be exerting on your hand or palm. Okay, so you just to see 1 kilogram weight or 1 kg force, many students may feel difficulty once the units are not observed. Okay, na? So what do you do? It is applying some force, just you find the value and you substitute in the answer and formula and you get the answer, but answer may be wrong. Why? Because if you don't observe the units, because there is not a rule always that should be given in the newtons. They may give in the kg weight and kg force. Definitely you need to convert them into Newton. Okay, na? So here 1 kg weight is equivalent to what? 1 kg, how much accelerated downward to the towards the center of earth. That force is called 9.8 newtons. And 1 gram weight or 1 gram force, 1 gram into 980 centimeter per second square. So gram into centimeter per second square is dyne. So 980 dynes will come. Okay, na? And approximately G value if you take 10, no, then definitely you get this is as 10 newtons and this is as 1000 dyne. Okay, na? So this is what explanation related to units of force in different cases. And let us move on to the next slide. Let us see different types of forces here. So actually forces are classified into basically contact and non-contact forces. So based on the physical contact, okay, na? So first type of contact forces, which one object exert force on the other with the physical contact, such forces comes under contact forces here. Next category, non-contact forces, which means one object exert force on the other one from a large distance or small distance. But actually we don't find any kind of physical contact, even though it can exert force one object on the other one. So we can see one by one. First of all, contact forces which will come under contact forces means basically tension force, next to normal reaction, next to friction. And about this you will learn completely a new lesson actually in the coming parts. Okay, na? It is actually given as complete lesson, but we will give some introduction for tension and normal force, friction. Okay, na? Let us know one by one first of all. And next non-contact forces. Here under non-contact forces, gravitational force, electrostatic force, next to magnetic force. Okay, so these forces will exert one particle on the other particle without physical contact. Okay, na? Let us start with the contact forces first. So normal reaction and friction. Okay, it is a reaction force. One is friction will come, one is what normal come. So the resultant is called contact force here. This is force contact or contact force, and contact force is electrodynamic in nature. So actually friction arises due to electromagnetic interaction between fundamental particles of two bodies. So that's what here it is, its nature electrodynamic they are giving. So one component will come parallel, one component will come perpendicular. That perpendicular force only we can call normal force here, and it is always acts perpendicular to the surface. Okay na? So now next here R is equivalent to normal. Okay, R perpendicular equal to normal. Actually normal reaction we can call, normal force also we can call. Okay, so normal reaction, normal force, reaction force, everything will come as in this manner. Okay, next parallel force. Parallel force means here whenever one person is applying some force on the body to pull it, okay, some dragging force act opposite to motion, right? So that force only called here frictional force. It is actually parallel component for the contact between the surfaces. Okay, so this is what actually for how a contact force is divided into normal and friction force, right? Next, draw the normal reaction in the following cases. See, normal reaction is always perpendicular to the point of contact. So in this case you can see this is the point of contact. For this it should be a perpendicular. So this is what here it is indicated. So this is right answer. Next, here one cylindrical sphere, cylinder or sphere, whatever it is, and at this point one contact we find, at this point we find contact, and for that you can see normal perpendicular, here also normal perpendicular, right? Next, in this case here is the contact point we find, and for the contact it is a tangent actually. Okay, so for this tangent that normal forces must be perpendicular. So here you can see this is perpendicular, this is also perpendicular. So this is the way we can draw the normal reactions in different scenarios. Next, tension. So it is also comes under contact force only. When a particular, here it is wall given and it is been fixed with a string and it is pulling left side, suppose, sorry, right side. Okay, he was pulling right side. So this is point of contact. Okay, so now this point of contact respect to tension force acts away from this one, and with respect to this point of contact always away from this one. Okay, by means of action of thread, actually the force, here you can see the resistance of a string or a rope against any change in its original composition is called tensile force or tension. Resistance of a string, okay na, or a rope against any change in its original composition is called tensile force. Okay, whatever the change is going to be made in that rope or string, that is opposed by its character or resistance to the change by the rope, it is actually called what? Tension force. Tension is always acts away from the point or tied ends. Next, tension is always pulling in nature. Okay, now try to pull like this. And if you can see one more case also, this is a mass suspended with the help of a string. So this is point of contact we find. So upward it is try to pull upward, right? But it won't go because it is balanced. So downward force equal to upward force when acceleration is 0. Okay, so this is more about tension actually, right? It is also defined as one more point also, whatever the fundamental particles of the string, okay, will exert attraction or repulsion force on the fundamental particles of the object, and the interaction between them is also results the tension force. Okay, this is the way also we can define tension force. Next, different second case, non-contact forces means they will exert force on each other but very distant, okay na, long away, right? Such a forces are called non-contact. Examples I told you, gravitational force, electrostatic force and magnetic force comes under non-contact forces. Next slide we will see. A non-contact force is a which acts on object without coming physically in contact with it. Okay. So, here earth exert gravity on the moon, but actually there is not requirement of physical contact of earth with the moon. Okay. This is gravitational pull towards the earth itself, that is gravitational force. Next, here it is a horseshoe magnet. It is exerting force on the iron particles or magnetic particles. So, this is also no need to make a contact initially, but after pulling it they will attract, but initially they will influence it. So, there is not requirement of any contact. Such forces are called forces at a distance or forces, non-contact forces. So, example they have given gravitational, magnetic force and electrostatic force also. Okay. So, next weight force, right? If any particle we hold or we just make a throw upward, okay, then it is always pulled downward. Like in the previous example, moon is pulled towards the earth surface. Okay, so that force acting towards the earth on the particle is called weight force. Generally F equal to ma, but here particle is accelerated downward with acceleration equal to g. So that's what I equal to g, then F equal to mg. So, this force is called weight force or weight of an object. The weight of an object is of mass m near the surface of earth is mg, where g equal to 9.8, because on the surface g equal to 9.8 meter per second square we will take. It is always directed towards the center of earth, because every object is being pulled by the earth towards its center only. So, that force on every object is called weight force. Okay. So, we will see next slide. Here is the question. A particle of mass 0.3 kg, okay, mass 0.3 kg is subjected to a force F equal to kx with a k equal to 15 Newton per meter. So, units are valid, and what will be its initial acceleration? They have asked to find acceleration is how much, and if it is released from a point where x equal to 20 centimeter, okay, away from the origin, and we just follow with the equation F equals to kx they have given here, and we know from second law of motion, from the second law of motion, what we know, F equals to ma. So, F equal to what they have given, kx, and they are asking acceleration. So, kx by m, k value given 15, x value 20 into 10 power minus 2 and mass 0.3. Okay. So, we can take cancellation here, okay na. So, this comes out to be 5, and next to 5 to the 10 meter per second square, right. More clearly for the simplification, you can see 15 into 0.2 by 0.3, decimal cancel, 3 5s and 5 2s. Okay. So, this is the asked acceleration. So, it go with the initial acceleration of 10 meter per second square. Let us move on to next slide. Next question is, a force of 10 I cap, 15 j cap, 25 k cap acts on the body and produces acceleration 2 I, 3 j cap and 5 k cap in it, and what is the mass of the body they are asking. So, from the second law of motion, F equals to ma, okay, and mass they are asking, so F by acceleration. So, both magnitudes we want, okay na. And magnitude of a vector you might learn in the vectors lesson. So, it is a 3-dimensional vector. So, 10 square, 15 square, 25 square by divided by 2 square plus 3 square plus 5 square. So, here comes 100 plus 225 plus 625. 4 plus 9 plus 25. So this is 650, 200, 850, 950. Okay. So 25 plus 4, 29, 38. And striking off, it gives you 25. So finally 5 kgs of mass. Okay na? So generally what they are asking is important. Okay. So here it is mass, and don't worry, mass is a scalar. Even force and acceleration given in vectors also, no problem. We just convert their we find the magnitude and convert them into scalar. Okay na? So that is what we can able to find given mass, right? So let us move on to the next slide. A uniform force act on the body of mass 2 kg at rest means initial velocity 0. If the body makes a displacement of 20 meters in 4 seconds, s equal to 20 meters in time 4 seconds. And what is the force? They are asking force acting on the body, first one. Okay, now let us solve for the first one, and remaining will be solved. First, F means we want mass into acceleration, mass is given, acceleration we required. Okay, na? S is given and time also given. S time acceleration, related equation is equation of motion second, S equal to ut plus half at square. So from this equation, S equal to ut plus half at square, S is given 20 meters, initial speed is 0, plus half acceleration is a, and time is 4, so 4 square. So here 20, half a 16, okay na? This have to be 8, acceleration equal to 20 by 8. So 4 5s are 4 2s are 2.5 meter per second square. So this is the acceleration we got, and force required na. So simply force equal to mass into acceleration, 20 into 2.5, which is 50 newtons. Okay na? So now after this one, second part, if the force acts only for 5 seconds, how much time it is been acting? 5 seconds. Okay na? How far will the body move in 3 seconds after the force has ceased to act? Okay, which means force is acting for 5 seconds, which means 5 seconds after speed is how much? After 5 seconds force is going to be stopped. Okay na? So body move in, how far will the body move in 3 seconds after the force is ceased to act? Okay, so you need to get the concept here. So till first 5 seconds, here 5 seconds, and in the coming 3 seconds, where here f equals to 0 and here f is non-zero because force is acting on the body. So what is the speed of the body in these 5 seconds we need to find out. Okay na? So from this concept we can take, first of all, v equals to u plus at, initial velocity 0, okay na, plus acceleration we got 2.5 into time 5, okay, this is v. So we got 2.5 means 12.5 meter per second, okay, velocity at the end of 5th second where force is going to stop. After force acting stop, then it moves with constant speed. So definitely we can find out acceleration 0, then v equal to s by t you can use, that is distance equal to v into t, s equal to v 12.5 into 3, so 15, 7, 3, so 37.5 meters will come. Okay na? So this is the distance covered by the body in the 3 seconds after force ceased to act. This is the way we need to solve the question. Okay na? Thank you.